So if you guys remember last day, we were dealing with the situation in which we have a differential constraint. So the system is no longer holonomic, and we have a constraint that depends on velocities. And we saw that this can be solved in terms of the Lagrange multiplier method, and this gives us an extra advantage, which is that the Lagrange multipliers are related to the forces of constraints. They are related to the forces that are responsible for the differential constraint. And sometimes this can be a real advantage because it is through this method of Lagrange multipliers that we can get access to the generalized forces of constraints. Normally, for physicists, the forces of constraints are things that we are not interested in. We essentially, we always want to get rid of them, get them out of the way, because they make our problem more complicated. But for other people, like for instance, engineers or architects, the forces of constraints are very interesting because those are the ones that tell you whether a certain structure will support the weight that you put on them or not. Whether a beam is una viga, okay, will support the ceiling, the roof or not. And this is something that is very important. And so it's also interesting to see how, this method of Lagrange multipliers allows you sometimes to get access to these forces of constraints. So now, for instance, we're going to do an example. So the example that I like to look at is the following. So we have a hoop. This is the hoop. And this hoop is rolling down this plane, this inclined plane, without slipping. Okay? So it's rolling down without slipping this inclined plane. And this condition of rolling down without slipping translates into a differential constraint. If let me just call x this distance from the top, and I call r the radius of this hoop, then x dot equals r times the angular velocity, right? Where the angle theta is this angle here, right? So that's what it means, to roll down without slipping. There is a relationship between x, the velocity in terms of x, and the velocity, the angular velocity in terms of the angle theta. Now, this differential constraint, it's obvious there is a differential constraint because it is a constraint on the velocities. This differential constraint is actually a fake. It's not a real differential constraint because it's you can trivially integrate it, right? You could integrate this thing. You can integrate, if you want, integrate to x equals r theta plus constant. So it's actually not a real differential constraint. However, for reasons that you guys will see, we're going to treat it as if it was a real differential constraint. And we're going to take it like this. We're not going to integrate it, even though it is true that we can integrate it. I mean, the integral is just here. And this constant here is completely irrelevant because it's just, is the origin, okay? The origin in the theta angle, for instance. So we're going to treat it like this, and we're going to apply, the technique that we learned the other day. So this means that this constraint, differential constraint, obviously translates into this constraint, right? All I'm doing here is multiplying by dt, differential of time, okay? And I'm pulling everything to the left-hand side. So this looks like the constraints that we had the other day. Remember? These constraints right here. let me find them here. In fact, okay, in fact, because the constraint that we have does not have any time dependence in an explicit way, time is not explicitly here, it means that this is the same as, the virtual displacement is the same. Remember that when there is no explicit time dependence in the constraint, the differentials and the virtual displacement actually coincide. They agree. So this means that if we just compare this to the situation that we had a situation. Let's go back again. Right, these constraints right here. This means that we have a differential constraint, a sub x dx plus a sub theta d theta equals 0, in which a sub x is 1 and a sub theta is minus r. So that's exactly what we have. Okay? So now all we have to do is just consider this differential constraint, add it with one Lagrange multiplier to the equations, to Lagrange's equations, and solve the equations and see what happens, okay? But for this, first of all, we have to write down the Lagrangian. And the Lagrangian requires the kinetic energy and the potential energy. So anyway, so now I'm gonna, start, thinking about how to compute, how to write down the kinetic energy for a hoop which is rolling down the plane like this. Okay. Now, any questions so far? So the thing is that you guys have to realize that this is one of the examples that of the method that we treated last day. Is that clear?
Yeah.
Yes.
Okay, good. So now the kinetic energy. What is the kinetic energy of a hoop which is moving, which is rolling down the plane? Okay. How do I compute the kinetic energy of this system? Is a rigid solid, right? So therefore, how do I write the kinetic energy of such a thing?
The movement of the center of mass and then the rotational part of the kinetic energy.
Very well, very good. Yes. So tell me. So now, what is the kinetic energy of the center of mass?
1/2.
Yeah.
The mass.
Let's call it capital M.
And then the velocity of the center of the hoop.
Yes. And so if I call x this coordinate, that tells me, how far down this hoop has rolled. X dot squared. Very good. So that's the kinetic energy that corresponds to the center of mass. Now the fact that the hoop is rolling, is spinning, is turning.
So 1/2.
1/2.
The inertia momentum.
Yes.
And then the angular velocity square.
Which with this angle theta is theta dot square, right?
Yeah.
Now, does anybody remember what the moment of inertia of a hoop is around its center of mass? It's not that difficult, huh? Make a guess. It has a radius r, and the mass is m.
mr squared.
Yes, exactly. That's the right guess. Exactly. So that's what it is. So that's the kinetic energy. Good. Now, the potential. For the potential, we have to be a little careful because we have to take into account, what is this distance, right? So let me just take this distance. The distance of the center of mass, to the ground, okay? So the distance is two parts. First, this solid red arrow, and then there is the dashed red arrow. I'm going to change the color just since I can, use all these colors, all these beautiful colors. So I'm just going to use all these colors. So this is green. So that's to the center of mass, because that's what the center of mass is at the center. And so how much is this quantity here in red? Well, if we call L the whole length of the inclined plane, okay, and this is the angle phi, so let's call this L. So this is L. Okay, so this quantity here, this height, is nothing but L minus X times sine of phi. You agree with me?
Yeah.
Okay, so that's this part. Now there is still the green part, right? Because I have to take, if I take the origin of the gravitational potential here on the ground, so that's the ground. Okay, so I still have to worry about the green part. But notice one thing. So let's compute the green part as well. The green part I can also compute. If the radius is r, the green part is going to be r cosine phi. You agree?
Yes.
Notice that this is also phi. This angle here is also phi. So this height in green is r cosine phi. But notice one thing. Does the green part change if the hoop is up here or the hoop is down there?
No.
It's the same, right? And actually, this is what this formula tells you. R is fixed, for a hoop of radius r, and phi is also fixed for an inclined plane of angle phi. So actually, the green part is fixed, is a constant. And I know that I don't have to worry about constants added to the Lagrangian. They are not going to do anything. So I can forget about the green part. So the potential is mg L minus X sine phi. That's the red part. And mgr cosine phi, which is the green part. But this I could forget about if I want. They are not going to affect the equations of motion. Now the Lagrangian is t minus b, as usual. And so therefore this is 1/2 of mx dot squared plus 1/2 mr squared theta dot squared minus mg L minus X sine of phi, plus constant, if you wish. Okay, so equations of motion. Remember that the differential constraint with the corresponding Lagrange multiplier has to be added to the Euler-Lagrange equations of motion. Look, like here. Okay, so that's what I'm going to do next. And I have two equations, two Euler-Lagrange equations, one for x, one for theta. So I have to add, the corresponding, terms in both equations. So let's look at the equations of motion. So the equations of motion are the usual ones, right? So they're going to be, d dt partial of L with respect to x dot minus partial of L with respect to x equals 0, right? And this becomes mg sine phi minus m dot x double dot equals 0. But that is if the differential constraint was not there. Now we have to add a Lagrange multiplier to this thing. And this Lagrange multiplier, in this case, is lambda times 1, because a sub x is 1. Okay? So this means that here I actually have minus plus lambda, I think, with this sign. Okay? Now, that's one equation of motion. Second equation of motion is d dt partial of L with respect to theta dot minus partial of L with respect to theta equals 0 would be without the constraint, but now with the constraint, this is going to be lambda r. And if I take all these derivatives on this Lagrangian, what I get is minus m r squared theta double dot minus, there is no theta dependence, there is only dependence through theta dot. So, minus lambda r, because now I have this r equals 0. So I have these two Euler-Lagrange equations with the one Lagrange multiplier because there is only one constraint. And then I also have the constraint, of course. The constraint x dot equals r theta dot. And these are the three equations that I have to solve. Okay? Any questions up to now? So I'm just copying in these two Euler-Lagrange equations, just copying, the result that we had, in general here. Exactly the same. Any questions before I start solving this system, which is not going to be very hard?
No.
Okay, so let's solve this thing. In order to solve this thing, it's much better. It's advantageous to take the constraint and take one derivative. X double dot equals r theta double dot. And then, the constraint with the second derivatives links, the two equations. So if I call this equation number 1, so this one is equation 1, and this one is equation 2, then I can do 1 times r plus 2, and then the Lagrange multiplier, 1 times r plus 2 cancels the term with the Lagrange multiplier, and I immediately obtain that x double dot equals 1/2 of g sine phi. The mass cancels out. Okay? So that's already the answer. That's already the answer, for instance, that you would find if you would apply Newton's law, okay, for the acceleration. Okay? And once I have the solution for x double dot, of course I can come here to the first equation, for instance, and find the solution for lambda. Okay? So then I can go to 1, replace this solution, and quickly find that lambda is minus mg divided by 2 sine phi. Okay, so that's already the answer that we want. We found everything. Of course, theta double dot is x double dot divided by r. So if I know x double dot, I also know theta double dot. So that's it. From the point of view of solving the system, is already solved. But now let's see how this Lagrange multiplier is actually related to the force of constraints, to the force which is responsible for the constraint. In other words, the force which is responsible for the fact that the hoop is rolling down without slipping. And what force could be this one? What is the force that is really forcing, okay, the hoop to roll down without slipping?
The friction.
Exactly, it can only be the friction. So that means that this guy, lambda, has to be related to the force of friction. So the generalized force in the direction x, which is, remember, our inclined plane, remember that this is x. And if now we draw here the forces like, you know, Sir Isaac Newton would do. Okay, so this is center of mass. This is the weight, mg. This is the reaction, N, from the inclined plane. And then we have the friction. So let me just write here the friction. So this is the friction, F friction, okay? And let us see how this F friction is related to this Qx. Remember, the Qx is the force, and the force is lambda, so this Lagrange multiplier, times A sub x. So let's go back. It's lambda times the corresponding A. Not just lambda, but lambda times the corresponding A. In this case, A is 1. But in general, it could be something else. So this is lambda. So therefore, this, in this case, this is lambda. And so this is minus mg divided by 2 sine phi. So this has to be the force of friction. So let us see that this is actually what happens, okay? And to find this out, all we're going to do is just, solve again the problem, just, focusing on the force of friction, but the way Newton would do it. And Newton would just say the following. We just say that the moment of the force equals the moment of inertia around the center of mass times theta double dot, right? However, the moment of all the forces through the center of mass actually has only as the non-zero contribution friction, because the weight goes through the center of mass, so the moment is 0. The reaction N from the inclined plane also goes through the center of mass, so that's also give you a moment 0. And the only one which is non-zero is the force of friction. So this is actually the force of friction times the distance between the point of contact and the center of mass, and that's what we call R. That's the radius. Okay, so that means that the force of friction times R has to be the moment of inertia, which we said is mr squared, theta double dot. Okay, so that means that the force of friction, of course, is mr theta double dot. But I already know what theta double dot is. Theta double dot is this guy here divided by R, right? So that is what? Is 1/2 mg sine phi. Perfect. So it is the same. Notice that the sign is the right one because the force of friction goes in the opposite direction, okay? So that's why there is a sign difference here. So indeed, the force of friction is given by the Lagrange multiplier, okay? So this is the lesson that we learned from this little exercise, okay? That sometimes it's useful to consider the constraints through Lagrange multipliers to get the forces Q, like in this case. Okay? All right, so questions?
Nothing, thank you.
Okay, so that's all we're going to do about differential constraints. Okay, now we're going to change subjects, and we're going to leave the Lagrangian and start thinking about the Hamiltonian. So that's Hamilton's formulation. So we move from the Lagrangian to the Hamiltonian. And what are the advantages of considering the Hamiltonian? First, it'll be first order differential equations. Instead of second order. Second advantage, it's the door, so the entrance is the door to canonical transformations. And symmetry. Symmetry will be something very important for us very soon. And canonical transformations are related to the symmetry. And canonical transformations are more easily formulated in terms of the Hamiltonian. But I mean, it's obvious that there is one advantage, which is one formulation of quantum mechanics. And actually, it is not just one formulation, it is the formulation that you guys are most familiar with, right? In quantum mechanics, we talk about the Hamiltonian. Is the Hamiltonian which becomes an operator? Is the Hamiltonian that you guys always want to diagonalize and not the Lagrangian? Now you know that there is another formulation of quantum mechanics, which is the path integral formulation of Feynman's, that, you know, in which the Lagrangian plays the main role. But that still, you know, doesn't say that, you know, the Hamiltonian is not very important, because it gives you the canonical formulation of quantum mechanics, right? So it is important to see, you know, how the Hamiltonian, you know, behaves relative to the symmetry, how the Hamiltonian, you know, controls the symmetry, what the Hamiltonian has to do with the symmetry of a problem, okay? And this is also true in your formulation of quantum mechanics. But we have to remember, as a matter of principle, no matter what we do, okay, the Hamiltonian formulation is not superior to the Lagrange formulation. It can be more convenient, or it can be easier for some things, but it's not intrinsically superior to the Lagrange formulation, but just more convenient for certain things, for certain things. Okay, so that's why we're going to study it now. And so let's compare the two formulations. Comparison. Lagrange Hamilton. Okay, so the function in the case of the Lagrange formulation and in the case of the Hamiltonian formulation. So the function in the Lagrange formulation is the Lagrange function, Q dot, and T. Okay, let me just write more clearly. And in the case of the Hamiltonian, is another function which depends on Q, P, which I will have to define, and T. Okay, equations of motion. So those are Euler-Lagrange equations of motion, partial of L with respect to Q dot minus partial of L with respect to Q equals 0, I equals 1 to N. And here it is Q dot equals partial of H with respect to P, and P dot equals minus partial of H with respect to Q, I from 1 to N. Okay? Where P, by definition, is the derivative of L with respect to Q dot I. Okay? So in the Lagrange formulation, these are a set of N second order differential equations. And in the Hamiltonian formulation, these are a set of 2n first order differential equations. Okay? Now, the space in which the solutions live is also different, at least in name, okay? For the Lagrangian formulation, we have the generalized coordinates, Q1, Q2, all the ones that you have, and here there is time. And so a solution is a trajectory in this space. This space is called configuration space. Configuration space. Whereas the solution in the Hamiltonian formulation, time is also here. But now we have the generalized coordinates and the generalized momentum, P, right? So, and all the ones that we have. We can have, 25 of these Qs and 25 of these Ps. And this is called phase space. Okay? So this is just nomenclature, names. And now we have to see how we go from the Lagrangian to the Hamiltonian. Okay? So we start with the definition of the canonical momentum P. Sometimes people omit the word canonical and they just call it momentum P, which is the variable that we have in the Hamiltonian formulation, which we do not have in the Lagrangian formulation, okay? And sometimes we can also call it canonically conjugate momentum, okay? Canonical momentum P or canonical conjugate momentum P. Conjugate to Q is conjugate to Q, conjugate to somebody. In this somebody is Q, conjugate to Q. Okay, so the definition is for a given generalized coordinate Qj, we define Pj as the derivative of L with respect to Q dot J, the corresponding velocity to Qj. And this, in general, is going to be a function of all the Qs and all the velocities, and why not, maybe also time, okay? And that's has to be true for all J from 1 to N. That is to say, each and every one of the generalized coordinates Q has to have a P so defined, a canonical momentum P defined in this way. So that's one condition. All the Qs have to have the corresponding P. And this is very important. This is very important. This equation has to be invertible. Oops. invertible for Qj. For Q dot J, sorry, for Q dot J. That means from this equation, I have to be able to invert Q dot J in terms of Pj. And this will be very important. It's crucial. Okay, it's crucial for the construction. Let me just rewrite this thing like this. Okay, so let's see. With this definition, let us see how we construct the Hamiltonian. Legendre transformations. And Hamilton's equations of motion. Okay, so given a system described by a Lagrangian, L function of Q, Q dot, and T, for all of them, J, J, and T. We define the Hamiltonian H of Q, J, P, J, and T as the Hamiltonian function of Q, J, P, J, and T equals the sum from J equals 1 up to N, all of them, of Pj Q dot J minus the Lagrangian of Qj, Q dot J, and T. So that's what the mathematicians call a Legendre transform. Transform of L. So the Hamiltonian is the Legendre transform of the Lagrangian. And notice here something important, which I already said in the previous slide, and I'm going to repeat again. I'm going to emphasize it again because it's crucial. Notice the dependence of the Hamiltonian. The Hamiltonian depends on Q, P, and T, even though the right-hand side is naively written in terms of Q dots. But this is a fake. This is not true. This Q dot here and this Q dot here have to be written in terms of the corresponding Pj using the inverse of the definition. Pj equals partial of L respect to Q dot J, which is a function of Qj, Q, oh, let's call it something else because it doesn't have to be the same, but all the Qk's, Q dot K's, and T. And this is a P, it's the same P. Somehow it appeared calligraphic, but it's the same. Okay? So that's what it means. It means that, yes, you write the Legendre transform like this. You write here P times Q dot J. There is a J, you know, from 1 to N. That means that there is a P for each Q, as I said before. But also, this Q dot here is not a real Q dot. It has to be written by inverting this equation and then replacing it in here, both in the dependence in the Lagrangian and in the dependence in this first term. And that's how you define a Hamiltonian. If you don't invert this thing, you're making a big mistake, okay? So there is a condition for this inversion. Is the inverse, right? So the inversion yields, or more than yields, requires. This inversion property requires. What is the condition to be able to invert this thing? So this is a mathematical question. What is the condition for this to happen? That was a question. What is the condition for this inversion to be realized, to be a possibility, to be true?
The Lagrangian to depend in some way of Q dot, maybe?
Yes, no, but look at this equation now. The equation that says that P is a function of Q dot. All the P's are functions of the Q dots. And we have to invert this equation now. We have to write down the Q dots in terms of the P's. Right? So what is the condition? It's certainly a condition on the P's, on the functions, these P functions.
They have to be smooth functions.
Yes, but that's not enough. Yeah, I mean, smooth is a good idea because it tells you something about the derivative. But there is an answer to this question. What is the condition on the function P to allow the inversion, of Q dot in terms of P?
It has to depend on Q dot.
Yes, and how you say that in mathematical terms?
I mean, if you are you looking for condition that derivative Pj over Qj have to be Qj dot have to be non-zero?
A condition for what? What's the word that you said?
I mean, derivative Pj.
Yes, exactly. Yes, that's the condition. Thank you very much. So the answer to this, exactly, you're right. So the answer to this question is given by the inverse function theorem. Remember? There is the implicit function theorem and the inverse function theorem, which are actually related, very related to one another. So the condition for this to be invertible is that the derivative of P with respect to Q dot is different from 0. So that's what one of you said, that P has to depend on Q dot. If P does not depend on Q dot, therefore, obviously you cannot invert. But now we have more than one, right? We have, n Pj's and n, Qk's or Q dot k's. So therefore, there's going to be a whole bunch here of derivatives of one of the P's with respect to all the other Q dots, right? So it's going to be derivative of Pi with respect to Q dot J. So now we have a matrix. So what is the condition now for this matrix? So what is this matrix called? Now we have a matrix, Ij. That's the entrance Ij. What is this matrix called? So that's the matrix Mij.
It's a Jacobian.
Exactly, it's a Jacobian. So now, what is the condition on this Jacobian?
The determinant has to be non-zero.
I cannot hear you. You have to speak closer to your microphone.
The determinant has to be non-zero.
Exactly. Very good. So that's a condition. This determinant has to be non-zero. Okay? Good. So this is the Jacobian, is an n by n matrix. So we have to have this condition. Otherwise, we cannot construct the Lagrangian. And there is another obvious condition. In order to write down a Hamiltonian for a system, what do we need? In order to write down a Hamiltonian to describe a system, what do we need for this system? What is the first thing that we write?
The Lagrangian.
a Lagrangian. So the system has to be described by a Lagrangian. If the system is not described by a Lagrangian because it has, some, force of constraints that, that don't allow you to write down a Lagrangian for them in any way, right? Because this may happen, right? Remember that sometimes, if the generalized forces do not derive from a generalized potential, then we have, we don't have a full description with a Lagrangian. Then we're going to write down a Hamiltonian either, okay? But if the system is described by a Lagrangian, then this is the definition of the Hamiltonian. And now we're going to see what the equations of motion are in terms of the Hamiltonian, okay? So let's do that. The equations of motion. What are the equations of motion? Well, let's take the Lagrangian. The Lagrangian is a function of q, q dot, and t. And actually, let's write down here the full dependence, q of t, q dot of t, and t, right? Because there is the full time dependence is through the q's and q dots, and also there may be an explicit time dependence. Okay, so let's compute the differential of L, and this is going to be the derivative of L with respect to qj times dqj plus the derivative of L with respect to q dot j dq dot j, this sum from j equals 1 up to n, and then the derivative of L with respect to t dt, right? That's the differential of these functions, a function which depends on q, q dot, and t. So therefore is the derivative with respect to q, derivative with respect to q dot, and derivative with respect to t times the corresponding differentials, of course. Now, what is the LDQ? What is the LDQ? This we can write in terms of p. Now we have to rewrite everything in terms of p's, okay? So we have to go back to the definition of p, the canonical momentum, and rewrite everything in terms of p. So that's our work now. So let's look at this first term. We know that the derivative with respect to time of the derivative of L with respect to q dot j equals the derivative of L with respect to qj, because these are the Euler-Lagrange equations of motion, right? So I can use this relationship here and say that this is the derivative with respect to time of, who is the derivative of L with respect to q dot? That's precisely pj. So here I already have a p, which is what I want. Okay, so this derivative here I can write as derivative of, well, actually I can just write it in a simpler way, p dot j. Okay, so I have p dot j. Okay, so then I have that this is the sum from j equals 1 up to little n of p dot j dqj plus pj dq dot j. And then the explicit time dependence. Okay, good. Now, Hamiltonian, function of q of t, p of t, and t, I, and this is the sum from j equals 1 up to n of pj q dot j minus the Lagrangian of q, j, q dot j, and t. All right, so now let's take the differential of this thing. And this is the sum from j equals 1 up to n of the first term is dpj q dot j plus pj dq dot j minus dl, but dl is written up here. So this is minus the sum from j equals 1 up to n of p dot j dqj plus pj dq dot j minus derivative of L respect to t dt. All right? Now, notice now that this term cancels this term. It's exactly the same. Okay? This term cancels this term. And therefore, the differential, so let me just make it very explicit, differential of the Hamiltonian function of q, p, and t equals the sum from j equals 1 up to n of q dot j dpj minus p dot j dqj minus the derivative of L respect to t dt. And this equation now is going to tell us what we want, okay? Because this equation now, it is really a differential of the Hamiltonian, okay, in the right variables, because the right variables are q, p, and t. And now I do have the differentials dp, dq, and dt, the right variables for the Hamiltonian. Before I didn't have this. Before here, I still had, the differential of dq dot, and dq dot is not one of the variables of the Hamiltonian. So therefore, at this level, before I could cancel these two terms, I had a mess. Okay, now I don't have a mess. Now I can really identify each and every one of the terms because the variables are the right ones for the Hamiltonian. So this means that this guy here and this guy here necessarily have to be the corresponding derivatives of the Hamiltonian. So q dot j has to be the derivative of the Hamiltonian with respect to pj, and minus p dot j has to be the derivative of the Hamiltonian with respect to qj, right? Because the differential of the Hamiltonian is obviously the sum from j equals 1 up to n of the derivative of the Hamiltonian with respect to pj dpj plus the derivative of the Hamiltonian with respect to qj dqj plus derivative of the Hamiltonian with respect to time dt. Okay? And then I can just identify term by term. And the last one is that the derivative of the Hamiltonian with respect to time equals minus the derivative of the Lagrangian with respect to time. So these are the equations. These are Hamilton's equations. Nothing but that. Okay? Any questions as to how I derived this?
Well, Paris, I do have a question, but regarding the previous slide, and it is that if, for example, I have a force that does not derive from a generalized potential, then I cannot write in the Hamiltonian. I cannot write the Hamiltonian.
No. If you don't have a Lagrangian, you cannot do the Legendre transform, and therefore you don't have a Hamiltonian.
Okay, so I should stick to Lagrangian methodology.
Yes, but in a case in which you don't have a Lagrangian, right? So you will have to do something else.
Okay.
Right? A Lagrangian, alone will not give you the answer. You will have to have, generalized forces or something.
Okay. Thank you.
Okay. So we just obtain, Hamilton's equations, okay? Just by doing this thing. And notice one important result, which is this one here, which is that the explicit time dependence of the Hamiltonian is directly related to the explicit time dependence of the Lagrangian. So if the Lagrangian is such that there is no time dependence, explicit time dependence, I mean, not the time dependence through the variables, q and q dot, but the explicit time dependence t. And remember, this had to do with the fact that the constraints would have explicit time dependence. So I say, if the Lagrangian does not have explicit time dependence, then the Hamiltonian doesn't have explicit time dependence either, right? If this one is 0, this one is also 0. straight away, directly. All right. So that's a simple thing to remember, and it'll be very useful. So let's repeat Hamilton's equations of motion, because they are going to accompany us for a few days. So that's Q dot J equals partial of H with respect to Pj. Remember that this is a function of Q, P, and T. And P dot J is minus the derivative of H with respect to Q, J, function of Q, P, and T. Remember, Hamiltonian, always a function of Q and P and T. So this cannot be the derivative of H with respect to Q dot, for instance. That would be a complete catastrophe, right? You cannot take the derivative of H with respect to Q dot because H does not depend on Q dot. Okay? And another thing which is a trivial kind of thing, but I think it's easy to fix, a possible confusion that you might have. After a while, you might start thinking, what is this minus sign, here or here, here or here, right? And which is the derivative that I have to take? H with respect to P is Q dot, or H with respect to Q is P dot? So what is this thing? So, example. Remember always this simple example. The Hamiltonian given by P squared divided by 2m plus the potential. In one variable, just the simplest case. You know that the velocity, which is x dot, is the derivative of h with respect to p, because that is p divided by m, and that's the velocity, right? And you also know that p dot, which is the force, is minus the derivative of the potential with respect to x, and that is the same as minus the derivative of the Hamiltonian with respect to x, right? So this, remembering this thing, will fix you this sign, and who is taking the derivative with respect to who, okay? So you don't get confused. All right, so that's just a simple reminder. So is a trivial remark. So let's forget about this, because you guys will always remember this thing for the rest of your lives, right? Okay. Now, how do you solve these equations? Those are Hamilton's equations of motion, but what do you do to solve them? Well, what do you do to solve them is you take this equation here, minus dh, at least in principle, then in practice, you do what you can to solve differential equations, right? You take this equation and you solve it, solve it for P, right, in terms of Q, right? So you take this differential equation, it's a first order differential equation for P, so you solve it given Q, given a Q in terms of Q, and that will give you P as a Pj as a function of Q and the other piece if necessary, okay? And then you come here, then you come to Q dot J equals partial of H with respect to Pj, which is a function of Q, P, and T. And you come with this equation, you put it here, and then this becomes an equation, differential equation for the Qs, and then you solve for Q of T, okay? For Qj of T. And this you can do for all of them. So that would be a possible strategy. I mean, I cannot deny that in practice, this is not going to be easy to do analytically, but that would be a strategy to do it if you were to solve these equations numerically, okay? All right, now, remember that other condition that I emphasized, right? The condition that said that the explicit time dependence of the Hamiltonian is minus the explicit time dependence of the Lagrangian. Right, so this is very important. Now we're going to see another result, which is even more important, which is let us compute the total time derivative of the Hamiltonian. So that is the total time derivative of the Hamiltonian, which depends on Q, which depends on T, depends on P, which depends on T, and there is also the explicit time dependence. So the previous partial derivative of H with respect to T would only take the derivative with respect to this T. But now I'm taking the derivative with respect to the whole dependence of T, which is here, here, and also here. Okay? So what is this? Well, chain rule. What does the chain rule say? I have to take the derivative of the Hamiltonian with respect to Qj times the derivative of Qj with respect to time. So that's the first term, j from 1 to n. But p also depends on time, so that is the derivative of h with respect to pj times p dot j. And finally, plus the explicit time dependence with respect to time of the Hamiltonian. All right, so any questions as to how I applied here the chain rule? It should be pretty straightforward, no? Anybody would like to ask anything?
All right, thank you.
No? Okay, good. So now let us look at the first term. What is partial of h with respect to q? On the equations of motion.
Minus pj, p dot j.
Minus p dot j, p dot j. Huh? Okay. And what is partial of h with respect to p? On the equations of motion.
Qj.
Sorry?
Q dot J.
Q
Qj.
dot j.
Q dot j.
Q dot j. Okay? So, all in all, what do we have? We have minus p dot j, q dot j, plus p dot j, q dot j. Huh. So that means that this guy cancels that guy. And this is very interesting because it says that the total time dependence of the Hamiltonian is actually the explicit time dependence of the Hamiltonian. This is very important because it says that if your Hamiltonian, which depends on Q, P, and T, if it does not depend on T, then H is what? What is H?
Stationary.
Yes, but what is the word for that? A simpler word, a more simple one.
Independent of the time.
In other words, what do you call something?
Conserve.
Exactly, is a constant. Is a constant, or if you wish, is conserved. Exactly. So if the Hamiltonian does not depend explicitly on time, it is a conserved quantity. Whether it is the energy or not, I don't care. It is conserved. And conserved quantities are very interesting. We are always, in looking for conserved quantities because they allow us to solve the problem in a more easy way, right? So this is very important. The fact that the total derivative of the Hamiltonian equals the partial derivative of the Hamiltonian with respect to time immediately tells us that if this is 0, then h is a constant and is a conserved quantity. Conserved quantity. Whether it is the energy or not, the conditions for the Hamiltonian to be the energy are different ones, and we'll look at them at some point. Actually, maybe today. Well, maybe not today, but the next day. Okay. So that's another thing. Another thing is the Hamiltonian the energy, the total energy of the system? Well, we will see. But regardless of whether the Hamiltonian is the total energy or not, if the Hamiltonian as a function does not depend explicitly on time, then it does not depend on time at all. It's a constant of motion, constant of motion. All right. Good. Now, so let us look at an example. An example that I'm pretty sure that you guys must have already seen at some point. Okay, so let's just start with a Lagrangian, which is usual kinetic minus potential, which is 1/2 of m x dot square plus y dot square plus z dot square. So that means it is some system with mass m, is a point-like particle, which is moving in 3 dimensions under a potential which depends only, on the distance to the origin of coordinates. Okay, so that's a system that you guys have already seen. It's planetary motion. If B of r was the gravitational potential, this would be planetary motion for a planet of mass little m. Okay, good. Now, let us write this system in terms of spherical coordinates. So it's r sine of theta cosine of phi. Y is r sine of theta sine of phi. And z is r cosine of theta. Spherical coordinates. So we write x dot in terms of r dot, theta dot, phi dot, y dot in terms of r dot, theta dot, phi dot, and z dot in terms of r dot and theta dot. And the Lagrangian, so I'm gonna, I spare you the exercise. You guys have already done this several times in your lives, probably. And this is the answer. So this is phi dot square minus b of r. So that's the Lagrangian written in spherical coordinates. Okay. So now let's compute the Hamiltonian. Let's construct the Hamiltonian. So first of all, canonical conjugate momentum to the r variable. So that's dl dr dot, and this is mr dot. Next one, p theta, that is dl d theta dot, and that is mr square theta dot. And finally, p phi, which is dl d phi dot, and that is mr square sine theta square phi dot. Okay, Hamiltonian by definition is PR times R dot, so that's the Legendre transform, plus P theta theta dot, plus P phi phi dot, minus the Lagrangian. So you compute. Remember that these equations here, so that's a square. No? These equations here are to be inverted, before you call the Hamiltonian a Hamiltonian, okay? And then once you invert all this, you compute all the terms, the result is 1 over 2m, so this is dot, 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 1 over 2m, p sub r square plus p sub theta square divided by r square plus p sub phi square divided by r square sine theta square plus b of r. Okay? Now, equations of motion. Let's compute the equations of motion. That is, r dot equals partial of h with respect to its corresponding canonically conjugate momentum, p sub r. And now, if I take the derivative here, it is nothing but p sub r divided by m. Theta dot. So that's, again, the same story. It's partial of h with respect to p sub theta. Okay, here is the dependence on p sub theta. So this is nothing but p sub theta divided by m r squared. Phi dot equals partial of h with respect to p sub phi. And this is p sub phi divided by mr squared sine theta squared. All right, next, PR dot, right? This is minus partial of h with respect to r. And this is a little more complicated because there is r dependence here, here, and in the potential, right? So this is 1 over m r cubed times p sub theta squared plus p sub phi squared divided by sine theta squared. This is squared. Okay. Close parentheses minus now the gradient of v with respect to r. P sub theta dot is minus dh d theta, and this is p sub phi squared divided by mr squared sine theta squared, and this is cotangent of theta. And finally, p sub phi dot, which is minus derivative of h with respect to phi. And whoop, surprise, lo and behold, here there is no phi dependence, so this is 0. Okay? And so we find that, and this is something that we will have to discuss also because this is related to asymmetry, the fact that the Hamiltonian does not depend on one of the variables, phi. This is what, you know, people call that the Hamiltonian, that phi is a cyclic variable, right? So this means, this here means phi is cyclic. Phi is cyclic. So h does not depend on phi, all right? And whenever the Hamiltonian does not depend on a certain variable, the corresponding consequence is that there is a canonical conjugate momentum whose derivative is 0. So that means that p phi is a constant. So that means that p phi is a constant. And again, we are very interested in constants of motion, right? Constants of motion. Like we already found one consequence for the Hamiltonian before, when the Hamiltonian does not depend explicitly on time. Now we find another consequence, which is that a canonically conjugate momentum is constant whenever the Hamiltonian does not depend on the conjugate variable, okay? So who is this p phi? Who is this p phi in other terms?
The angular momentum.
Yes, exactly. So this constant is the angular momentum. Is the angular momentum. Okay, so you guys already know this. So now, what we are going to see is that these equations of motion, Hamilton's equations of motion, are actually equivalent to Lagrange's equations of motion. And this we will see only in one example. Okay, so let's look at one of the Lagrange's equations of motion. Lagrange's equations of motion. So I'll look at one of them, which is the equation of motion for R, for instance. I have the Lagrangian here. So I can apply Euler-Lagrange equations of motion to this Lagrangian. And for R, the equation is this one. Is mr theta dot square plus sine squared theta phi dot square minus the derivative of the potential with respect to R, and etc. for the other two, right? For theta and for phi. But let us look at this one. And let us look now at Hamilton's equations of motion, okay? And we see that we can also write mr double dot as, well, we come here, we look at this equation, and we see that mr double dot is going to be pr dot, right? mr double dot is pr dot, and the m goes to the other side. But pr dot is written here. It's 1 over mr cubed times p theta plus p phi squared divided by sine squared theta minus dv dr. If I input here, I replace p theta by what it is. P theta is here, written in terms of theta dot, and p phi is here, written in terms of phi dot. Then I'm going to find So before I find 1 over mr cubed p theta squared plus p phi squared divided by sine theta squared minus dv dr. And now replacing p theta and p phi in terms of theta dot and phi dot, what I find is mr theta dot squared plus sine theta squared phi dot squared minus dv dr. And that's exactly what it had to be. This is the same as this. So, okay, so you'll find exactly the same equations of motion, right? Whether you write it in terms of the Lagrangian or in terms of the Hamiltonian, all right? And you can do the same thing for the other two, for the equations of motion for theta and for phi. So this is just an example of how you construct a Hamiltonian. I'm sure you have seen this thing when you guys discuss planetary motion. So that's it for the example. Now we're going to start discussing something that I mentioned before. I mean, any questions about this? This is, I believe this should be quite straightforward. But if you guys have any comment or any question, please ask. Any questions?
No.
Okay, good. Right, so now we're going to start discussing what is the relationship between the Hamiltonian and the total energy. Relationship between the Hamiltonian and the total energy. There is a question? I couldn't hear well, so is there a question? Hello?
No.
Okay. No, I thought that somebody wanted to ask something. Well, anyway, so what is the relationship between the Hamiltonian and the total energy? Because there are systems in which they are the same. The Hamiltonian is the total energy, but not always. So what is the general condition for the Hamiltonian to be the total energy of the system? And the system doesn't have to be very strange for the Hamiltonian not to coincide with the total energy. Huh? I mean, a system in which the total energy is not the Hamiltonian is a particle in an electromagnetic field. So it's not that strange, right? So you don't have to go to a very complicated, and contrived system for this H and the total energy to be the same. It is not. For a particle in an electromagnetic field, as we will see, they do not coincide. They're not the same. So what is the general condition for this? Well, let's compute the kinetic energy. First, right? And then we compute the potential, and if we sum them, we're going to know the total energy. So we go to the beginning. We had a system with, Cartesian coordinates written in terms of generalized coordinates in a holonomic system, right? After we solved the constraints. That's how we started. That's how we defined, actually, the generalized coordinates, right? So if we want to compute the kinetic energy, we have to take the derivative of this, which is the velocity. We have to square it, multiply by 1/2 times the mass, and sum. And that's going to be the kinetic energy. And what comes out, comes out. Okay, so let's see what comes out. So the velocity is the derivative of each of these r's with respect to time. And given this dependence, this is the sum from j equals 1 up to n of the derivative of each position vector with respect to qj times q dot j. That's the chain rule. And if there is explicit time dependence, then this is the partial derivative, right? What is the kinetic energy? Well, it's the sum from I equals 1 up to n. So let us consider n particles. And let us consider little n generalized coordinates. Right? So the generalized number of generalized coordinates is the number of degrees of freedom that I have, which is 3 times capital N minus the number of constraints. The number of constraints, I don't care here. I mean, whatever. I mean, the important thing is the dependence of the position vectors on the generalized coordinates. So now the kinetic energy, therefore, is the sum from 1 up to capital N, because I have n particles, of 1/2 times the mass of each particle times each velocity squared. And in this case, this is 1/2 of the sum from I equals 1 up to capital N of the mass of each particle. And now I have to square this. I have to square the velocity, okay? So if I square the velocity, since the velocity v depends on q dot plus something, I'm going to have a term with q dot, I'm going to have a term with q dot, and I'm going to have a term without any q dot, right? Depending on whether I square this thing, I multiply this times this, or I square this thing. So that the answer is sum from j equals 1 up to n, sum from k equals 1 up to n, of the derivative of Ri with respect to Qj, derivative of Ri with respect to Qk, Q dot j, Q dot k. All right? That's the first term, the square of the first guy, plus. And now it's going to be the cross term, q dots times this guy. And there are two of them, right? This square of this plus twice this times that plus the square of that. Okay, so that's plus twice the sum from j equals 1 up to n of the derivative of Ri with respect to Qj times Q dot j times derivative of Ri with respect to t. All right? And finally, plus derivative of Ri with respect to t squared. All right? Questions about this? Obviously, the sum over I is nothing but this, you know, the dot product, this, what we say, we call this the scalar product of dri, right? So that's the sum over I. So that's through here, that's also through here. Remember that there is a Ri, and also here, this is dri. Okay, so it's the scalar product of dri respect to t, or which is what I write as dri squared. I hope that this is not confusing in any way. Any questions about this?
No.
Okay, everybody would know how to square this thing like this, huh? With all the sums and all the things. Well, all right.
Yeah.
Okay, good. So let us write this thing in a way which is going to be more transparent. Okay. All right. So I multiply the 1/2 and I write this thing as the sum from j equals 1 up to little n, sum from k equals 1 up to little n, of 1/2 of the sum from I equals 1 up to capital N of mi, derivative of Ri, derivative of Ri with respect to Qj, derivative of Ri with respect to Qk, times whole thing times Q dot j, Q dot k. So that's the first guy. I just pull this sum from I equals 1 up to capital N inside, okay? And I pull out all these two sums with respect to j and k. Okay, and now The linear term in Q dot is going to be the sum from j equals 1 up to n of the sum from I equals 1 up to capital N of M sub I, derivative of Ri respect to Qj, derivative of Ri with respect to T times Q dot J plus 1/2 of the sum from I equals 1 up to capital N of M sub I, derivative of Ri respect to T, whole thing squared. So that's what I have. Okay? So what do I learn from this? What I learned from this is that the kinetic energy, in complete generality, okay, for any system written in terms of generalized coordinates, has a quadratic term in terms of the generalized velocities. It has a linear term in terms of the generalized velocities, and it has a term which is independent, completely independent of velocities. Okay, completely independent. Okay, so this is quadratic. Quadratic in Q dot. This one is linear in Q dot, and this one is independent of Q dot. Okay, so this is important. So this has the kinetic energy is a quadratic form, right? It's a quadratic form in mathematical terms. It's a quadratic form. Okay. Now notice another thing. What happens if the constraints do not depend explicitly on time? We always have to look at this because systems for which the constraints do not depend explicitly on time have nice properties, right? Like, for instance, the Hamiltonian, okay? The Hamiltonian would be a conserved quantity and things like this. So we always have to look for the situation in which what if the constraints do not depend explicitly on time? That would mean that these R's, the position vectors, would not depend explicitly on time. But if this is the case, then this derivative is 0. So this and this would be 0. So T1 equals T0 equals 0, which is the important thing, if the derivative of Ri with respect to T is 0, which is constraints do not depend explicitly on T. Okay? So that's something very important. So the kinetic energy collapses to just, the term which is quadratic in Q dot if there is no explicit time dependence in the position vectors written in terms of the generalized coordinates. All right? Now, we are going to assume, let's assume that not just the kinetic energy, but the whole Lagrangian can be written in this form. So there is a quadratic in Q dot, there is a linear in Q dot, and there is an independent of Q dot terms, okay? A quadratic term in Q dot, linear term in Q dot, and a term which is independent of Q dot. Obviously, this would be T2 plus T1 plus T0 minus V2 minus V1 minus V0, right? Because L2 is going to be T2 minus V2, right? So L2 is T2 minus V2, L1 is T1 minus V1, and L0 is T0 minus V0, right? Because, the whole Lagrangian splits into quadratic, linear, and independent of Q dot terms. Good. So now with a Lagrangian like this, that splits into quadratic, linear, and independent terms of Q dot. We want to compute the Hamiltonian now, because this is going to tell us whether the Hamiltonian equals the energy or it doesn't equal the energy. All right? So the Hamiltonian, by definition, is the sum from j equals 1 up to n. We're summing over all generalized coordinates and conjugate momenta. So this is pj q dot j minus the Lagrangian. All right. So this is the sum from j equals 1 up to n of the derivative of the Lagrangian with respect to q dot j times q dot j minus the Lagrangian. But now I'm telling you what the Lagrangian looks like, right? The Lagrangian has a quadratic term in q dot, a linear term in q dot, and an independent term of q dot. So can I compute here? Can I write here, you know, what this is going to look like in terms of L1, L2, and L0? Who can tell me what this is going to look like? So minus L. So the minus L is going to be minus L2, minus L1, minus L0. This is clear, right? Because if L is L2 plus L1 minus L0, minus L is this. This is obvious. There is no question about this. But what is this first term? This first term. What is the derivative of L with respect to Q dot times Q dot when L has a quadratic term in Q dot? Who can guess what the answer is going to be?
2L2.
Absolutely. Very good. 2L2. And the next one?
L1.
Plus L1. And L0
It's 0.
is 0 because it's independent of Q dot. So absolutely. So yes, that's the answer. So now I would like you to take this sum like this, do the derivative explicitly, and check that this is true. That the L2, because it's quadratic in Q dot, give you twice L2, and the linear term give you, you know, the linear term itself. All right? So I'm going to leave this thing as an exercise. This is an exercise. It's an exercise in what is called index gymnastics, right? So just take the derivative. It's very simple, huh? But do it. Do it. Now we are in a position to see something interesting, which is the L1 cancels out. The L2 almost cancels out, leaves from 2L2 you get L2, and then you get L0. So the Hamiltonian knows nothing about the linear term in Q dot. So this is going to be interesting, okay? H does not depend on L1. Okay? So that's all for today. Any questions or comments?
No.
No? Okay. Well, thank you then.